it was p hat plus or minus the margin of error. And you might not remember this, and it's okay if you don't, because we didn't have to use it very much. We're using technology quite a bit these days. The margin of error calculation was made up of the p hat and the q hat, which is essentially kind of the same thing as x or s over here, the sample standard deviation. Under that was the sample size, if you remember. And this was the way we control. Did anybody get a chance to watch the videos on how that was derived? Was it elucidating? Maybe you didn't get a chance to yet. It's totally fine if you didn't. I made a quiz about it for this week, so you'll get into it and look. So as your sample size goes up, what happens to this? This whole thing. It shrinks, because it's in the denominator. Very, very nice. And then we attach on the outside a confidence meter of z. A confidence meter of z. We need something similar for means, don't we? We have to adjust that for means as well. So let me swing this back a little bit this way. So in other words, x bar is going to have plus or minus a margin of error as well. It's going to have plus or minus a margin of error as well, yes? And that needs to be adjusted for sample size. So let's break it down. Let's break it down. Let's see if we can figure out what it's going to be. It has something to do, Mel, you're 100% correct with the sample standard deviation. That's the best thing we've got. We've got an average, we've got deviation from that average. So we've got, by definition, that measurement to measure variance, or variation, I guess. So S. The problem is, that should shrink. That should shrink as the sample sizes get larger. So do you agree that we should have a fraction of some kind involving the sample size? Do you have any vote for what should be in it? Any idea? Should it just be divided by n? That would be nice. Unfortunately, it's not divided by n. It's divided by what? And you know the answer from 243. It's actually in that formula already in the sample proportions. This isn't really being divided by n. It's being divided by... This is Math 65 coming back to haunt you. I apologize. The n in that fraction is being square rooted, isn't it? It's under a radical. Remember from 243, you guys figured there's the last couple days of the term, and I apologize for pulling this out of nowhere. But when we had the big Excel spreadsheet on the board, and I had samples of size 1, 4, 9, 16, 25, and 100, and then the standard errors were shrinking by certain fractions, and you said, 4 is shrinking by a factor of 1/2. 9 is shrinking by a factor of 1/3. 16 is shrinking by a factor of 1/4. And you made a connection between those numbers and the sample size. How is 2 related to 4? 3 related to 9? 4 related to 16? 5 related to 25? Square roots. That was the takeaway from the central limit theorem. It's not divided by n, it's divided by the square root of n. One of the most fascinating results, I believe, in mathematics. It's tied to the square root of the sample size. Now, don't worry about memorizing that. You're going to see it almost every other day in this class. So if you don't memorize it now, you're fine. You'll get it beaten into you in the next 8 weeks. In a loving way, of course. I beat lovingly. The problem is, where it comes from is that the variance is actually divided by the sample size. But when you take the square root of the variance, you end up with the square root of the sample size and the standard deviation. Remember the variance from 243? I mentioned it once, maybe twice. Never mentioned it again. It didn't make any sense to talk about because we don't actually use it. We use this. And then we have a multiplier out front, a confidence multiplier, if you will. But let's come back. Let's adjust, first of all, let's adjust our intervals based on this, yes? Let's adjust our intervals based on this. Okay, let's swing back over here.